Hello students. In the last class, we learned about the basic types of main combustion chambers. In this class, we will learn about the basic components of the main combustion chamber. When learning about the basic structure and working process of the main combustion chamber, we said that the main combustion chamber is generally composed of a diffuser, a shell, a flame tube, a vortexer, a nozzle, and an igniter. Next, let's learn about the diffuser. The diffuser is a pipe that reduces the airflow velocity and increases the pressure. In addition to reducing the airflow velocity at the compressor outlet, it is also one of the main load-bearing components of the engine. In the annular combustion chamber, the diffuser also plays the role of distributing the two airflows inside and outside. Diffusers can be divided into three types, according to the different cross-sectional changes: primary diffuser, secondary diffuser, and sudden expansion diffuser. The picture shows the sudden expansion diffuser of the RB199 engine. Next, we will learn about the casing parts. In the annular tube and annular combustion chamber, the combustion chamber casing is composed of the inner and outer casings. The figure shows the combustion chamber casing of the WP7B engine. You can think about it. What is the function of the casing? The role of the casing is that, first, it forms two airflow channels. Second, it is the main load-bearing component, and sufficient strength and rigidity must be guaranteed in the structural design. In addition to selecting suitable materials and shell thickness, reinforcement measures must be adopted in the parts of the shell with poor rigidity. The commonly used and effective method is to use radial reinforcement ribs. Third, the outer wall of the casing can be installed with pipelines and accessories such as the engine, fuel, main pipe, branch pipes, etc. As shown in the figure, the flame tube of the WP6 engine is the main component of the combustion chamber and the place where combustion is organized. It is generally composed of a vortexer and a flame tube body. Flame tubes generally have two structural forms: sheet metal, welding, and mechanical processing. As shown in the figure, the flame tube of the WS9 engine is welded from several sections of sheet metal raw materials to form an air film cooling type flame tube. When this type of flame tube is working, an airflow flows along the inner surface of the flame tube to form an air film. Since the air film has the dual functions of heat insulation and heat dissipation, it has a good effect in reducing the temperature of the cylinder. At present, the air film type flame tube, formed by mechanical processing, has been widely used in the annular combustion chamber of large and medium-sized engines. This type of flame tube can design the flow channel of the two airflows more reasonably, further improve the heat dissipation effect of the air film type flame tube, meet the requirements of high heat capacity, strength of modern engine combustion chambers, and at the same time, the circumferential stiffness of the flame tube wall is uniform and strengthened. At present, there are more advanced floating wall flame tubes. As shown in the figure, the flame tube of the V2500 engine adopts an integral cast sudden expansion diffuser. There are 5 floating rings composed of butterfly-shaped floating plates on the inner and outer walls of the flame tube, which separate the high-temperature combustion gas from the inner and outer walls of the flame tube. There is a cooling airflow channel between the inner and outer walls of the flame tube and the floating plates. There is a heat shield at the head of the flame tube, which effectively insulates and cools, extending the fatigue life of the flame tube. As shown in the figure, there is a vortex finder at the front end of the flame tube. Its function is to form a reflow zone at the head of the flame tube, reduce the airflow velocity, form a stable fire source at the head of the flame tube, and mix the atomized fuel and air well, thereby improving combustion efficiency and ensuring stable operation of the combustion chamber. Next, we will learn about fuel nozzles. Fuel nozzles are components that atomize or vaporize fuel, accelerate the formation of mixed gas, ensure stable combustion, and improve combustion efficiency. They can be divided into centrifugal nozzles, pneumatic nozzles, evaporative nozzles, and oil slinging disc nozzles. As shown in the figure, this is the atomization principle diagram of the centrifugal nozzle. Under the action of oil pressure, the fuel enters the nozzle cavity along the tangential direction, rotates at high speed, and when it is sprayed out from the nozzle, it is atomized under the action of centrifugal force to form a rotating conical oil mist layer. The advantages of the centrifugal nozzle are that it can make the combustion chamber burn stably in a wide range of oil-gas mixture ratios, work reliably, have a solid structure, and be easy to debug, so it is widely used in branch and annular tube combustion chambers. The disadvantages are high requirements for oil supply pressure, the presence of high-temperature, oil-rich areas, easy to cause smoke pollution, and the combustion chamber outlet temperature field varies greatly under different flight conditions. Secondly, the annular channel of the annular combustion chamber does not match the conical oil mist of the centrifugal nozzle. As shown in the figure, this is the pneumatic nozzle of the PU 4000 engine. The pneumatic nozzle allows the oil film to interact with the high-speed airflow. Under the action of aerodynamic force, the oil film is broken and atomized, quickly forming a uniform and good oil-air mixture. The advantages of pneumatic nozzles are, first, the oil and gas are mixed evenly, avoiding local oil-rich areas in the main combustion zone, reducing smoke and carbon deposition. Second, pneumatic nozzles do not require very high oil supply pressure, and in a wider working range, it is easy to make the combustion chamber outlet temperature field distribution more uniform. The disadvantage is that at startup, the airflow, velocity and pressure are low, and the atomization effect is poor. Due to the full mixing of oil and gas, the lean flameout limit is reduced, which narrows the stable working range of the combustion chamber. Evaporative nozzles and oil slinging plate nozzles are less used, so we will not introduce them here. Finally, let us take a look at the igniter. The picture shows the igniter of the WP6 engine. The function of the igniter is to form an ignition source when the engine is started on the ground or after the engine is shut down at high altitude and ignite the fuel mixture at the head of the flame tube. Ignition forms are divided into direct ignition and indirect ignition. Direct ignition is to use an electric igniter to directly ignite the mixture at the head of the flame tube. With the development of high-energy electric igniters, the discharge energy of resistors at low voltages has been greatly increased. Therefore, direct ignition has been widely used. As shown in the figure, the igniter of the SPA engine adopts the form of direct ignition. Indirect ignition is to ignite the fuel of the starting nozzle, first forming a small flame, and then use the small flame to ignite the fuel sprayed from the working nozzle. As shown in the figure, there are two igniters of the WP7 engine, which are installed in the front of the outer shell of the combustion chamber. The igniter consists of a gasoline nozzle, an electric nozzle, an oxygen pipe joint, and a shell. In order to ensure high altitude, starting gasoline is used as the starting fuel. Students, in this class, we have learned the basic components of the main combustion. You should master the functions and classifications of each component in time after class and apply them to other situations. Thank you.